In the previous lecture, I have introduced you to two frame of references. The first one was laboratory frame, which is commonly called lab frame, and the another was center of mass frame. Okay, actually, our prime aim is to deal with the two-dimensional collision in these two frames. So I have started to dealing with the problem of two-dimensional collision in lab frame and the center of mass frame. In this lecture, we will see the two-dimensional perfectly elastic collision between two particles or two bodies in laboratory frame. And after that, in the second lecture, you will see the same problem in center of mass frame. Actually, this two-dimensional perfect elastic collision is a very important problem of classical mechanics. In several places, you find such situation, like you have definitely studied Compton effect or Compton scattering, where actually two-dimensional collision takes place between a photon and a free electron. Okay, so this problem is uh, of great practical importance. Okay, here in this lecture we will see the general concept how we can deal with the problem of two-dimensional perfectly elastic collision in laboratory frame. We will see in very detail in this lecture. This is just a theoretical basis and this concept is utilized in the physical problem. Okay, so let us see this figure. Actually, here I have shown that before collision, when the two bodies have not collided with each other, you can see I have considered this particle of mass m1 moving with a velocity u1 in x direction. Actually, this direction has been taken as x direction. Okay, and moving with velocity u1, this particle of mass m1 collides with another particle whose mass is m2, and I have considered that the second particle of mass m2 is at rest. So you can see in this figure that I have noted here that the velocity of this particle of mass m2, which is u2, that is equal to 0. Actually, when the particle of mass m2 is at rest and a particle of mass m1 moves towards the particle and collides with it with velocity u1 with respect to the laboratory frame, then we call this particle of mass m1 as projectile. That is the particle which will hit the mass m2, that is called projectile. So in this problem, you can say that there is a projectile of mass m1 moving with velocity u1 with respect to the laboratory frame, and it collides with another mass m2 which is at rest. Okay, then this m2 is called target. M2 is called target. Okay, and the target I have considered here is stationary. This is actually the situation when no collision takes place, or you can say that this is the situation of before collision. Now let us consider that this particle of mass m1 has collided with mass m2 which is at rest before collision, and the collision is perfect elastic. Actually, after the collision, I have shown in this second figure B, you can see that the projectile of mass m1 moves with a velocity v1, making an angle theta 1 with the initial direction of motion of m1. You have considered that initial direction of motion of m1 is along x-axis, so you can say that m1 moves with velocity v1 making an angle theta 1 with the x-axis. In this condition, this angle theta 1 This is called actually the angle of scattering. Theta 1, it is called angle of scattering. It means you can say that the angle made by the final velocity of the projectile with the initial direction of motion, that is called angle of scattering. So here this theta 1 will be called angle of scattering. On the other hand, you can see that the target which was at rest before collision, now it is moving with velocity v2, making an angle theta 2 with the initial direction of motion of m1, that is the direction of x-axis. Then this angle theta 2, which is actually angle of scattering for the target, but this angle of scattering for target is commonly called angle of recoil. This is called angle of recoil. Okay. Actually, the prime aim of this problem is to find the final velocities v1 and v2. Final velocities v1 and v2. It means if you know the initial velocity u1, you can find the final velocities v1 and v2. At the same time, in some problem, you also need to find the values of this angle of scattering theta 1 and the angle of recoil theta 2. Okay. And once you get the values of theta 1 and theta 2, you will be able to relate this theta 1 with theta 2. So the prime aim of this collision problem is what? This is to find the final velocities, to find the relation between the angle of scattering theta 1 and the angle of recoil theta 2. How these two angles are related, this is also found in this problem. Okay. Actually, you have studied the problem of collision in your lower classes in 11th level. You know that any problem of collision or scattering is solved by the use of different conservation principle, because in this case writing the equation of motion is not possible, because during the collision a very complicated impulsive force acts between the colliding bodies, and how that force varies with time, this fact can be not known easily. So you can say that a strongly time dependent impulsive force acts on the bodies which get collide, and the nature of that force, how that force is related with time, it is quite impossible to find. And that's why the problem of collision is never solved by writing the equation of motion, that is applying the second law of motion. So the mathematical tool to solve the problem of scattering or problem of collision is what? This is the technique of using the principle of conservation of linear momentum, principle of conservation of energy. These principles are actually applied to solve any collision problem. Okay, this is the common process. Now let us see how we can apply these conservation principles and how the problem can be solved. Here I have shown that this collision is taking place in xy plane. You can see the figure. In fact, before and after collision, the colliding bodies move in xy plane. So you can say that here the collision is two-dimensional, and this two-dimensional collision is taking place in xy plane. Okay. Now, as I have told you that this problem can be solved only using the conservation principle of linear momentum, the conservation principle of energy. Here, since the problem is elastic collision, and you have definitely an idea that during an elastic collision, the total kinetic energy of the colliding system before collision and after collision remains same. So using these two conservation principles, you can solve this problem. Okay. Now let us see how we can apply these conservation principles. Actually, what I have explained just now, I have written those facts here in brief. You can see I have considered that before collision, u1 which is equal to u1i, it means u1 is directed in x direction. This is actually the velocity of the particle of mass m1 which is called projectile, and the velocity of mass m2 which is called target is 0, u2 is equal to 0. But after collision, the velocity of the projectile becomes v1 and velocity of target becomes v2, and the angle of scattering is theta 1 and angle of recoil is theta 2. Okay, and we are considering the perfect elastic collision in xy plane. Now, since momentum is a vector quantity, so when you will apply the principle of conservation of momentum, you can think about the components of the momentum. Actually, the total momentum before collision and after collision in x direction and in y direction both will remain conserved. So, if you apply the principle of conservation of linear momentum for x direction, what will be your result? You can see. In fact, according to conservation principle of momentum, the total linear momentum of the colliding system initially, when you say initially, that means before collision. So total linear momentum in x direction before collision will be equal to the total linear momentum of the colliding system after collision, okay, in x direction. Now, since in our problem there are two colliding bodies, first one is of mass m1 and another is of mass m2, and when you talk about this collision process before collision, then you have seen that before collision only mass m1 is moving and its velocity u1 is already in x direction. Okay, so there is no need to resolve it because u1 is completely along x direction. So before collision, the linear momentum of mass m1 in x direction, or you can say that the x component of the linear momentum of mass m1 before collision, that will be simply m1 u1. Okay. Now m2 is at rest, so its linear momentum is 0, and if its linear momentum is 0, both of its x and y component will be 0. So the linear momentum of the target of mass m2 in x direction is 0. So before collision, total momentum of the colliding system before collision, that will be equal to m1 u1 plus 0. Okay. Now see the figure. You can see that the velocity of mass m1 is v1 after collision. So its momentum will be m1 v1. And you can see the figure. The component of this momentum m1 v1 along x direction, this will be what? This will be m1 v1 cos theta 1. Okay. And similarly, the x component of the momentum of m2, which is actually m2 v2 after collision, its x component will be what? This is along the positive x-axis, and this will be m2 v2 cos theta 2. You can see the figure. So the total linear momentum of the colliding system in x direction after collision will be sum of these two components, that is m1 v1 cos theta 1 plus m2 v2 cos theta 2. So you can see I have written that after collision, total momentum in x direction of the colliding system is m1 v1 cos theta 1 plus m2 v2 cos theta 2. Okay. and you can equivalently write it as m1 u1 equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2. So applying the principle of conservation of linear momentum for x direction, we have obtained this result. Okay. Now we will apply the same principle of conservation of linear momentum for y direction. Now see the figure. Since velocity of m1 before collision is u1 and it is directed in x direction, so what will be its y component? That will be m1 u1 cos 90, because with y direction it makes an angle of 90 degree, and that will be equal to 0. And the target is already stationary, so its total momentum is 0, and hence its xy component will be also 0. It means before collision in present situation, the total linear momentum of the colliding system in y direction is 0. Both the momentum of both of m1 and m2 are 0 in y direction. So I have written here, you can see that the total momentum before collision in y direction is equal to 0. Okay. Now again see the figure. m1 v1, this is the linear momentum of mass m1 after collision, and it makes an angle theta 1 with the positive x-axis. Okay. So the y component of this momentum will be what? This will be m1 v1 sine theta 1, and it is directed in positive y direction. And similarly you can see that the y component of the momentum of the target after collision, that is y component of the momentum m2 v2, this will be what? This is in fact m2 v2 sine theta 2. But since this component is directed in negative y direction, so you should write it minus m2 v2 sine theta 2. Okay. So after collision, total momentum of our colliding system in y direction will be what? That will be m1 v1 sine theta 1 minus m2 v2 sine theta 2. So you can see I have written here that this is m1 v1 sine theta 1 minus m2 v2 sine theta 2. So this second equation we have obtained by applying the principle of conservation of linear momentum in y direction. Okay. Now since we are considering the perfect elastic collision, and you know in case of a perfect inelastic collision, the kinetic energy of the colliding system before collision and the kinetic energy of the colliding system after collision are equal. It means kinetic energy in a perfect and elastic collision remains conserved. Okay. Now, what will be the total kinetic energy of this colliding system before collision? As you know, before collision only mass m1 is moving with velocity u1. So the kinetic energy of m1, that is that of projectile, that will be half m1 u1 square before collision. But since m2 is at rest, so kinetic energy of m2 will be 0. So I have not added that 0 here. You can see this a half m1 u1 square will be the total kinetic energy of our colliding system before collision. Okay. Since kinetic energy is a scalar, so there is no need to write vector equation here. Now after collision, velocity of m1 is v1, so its kinetic energy will be half m1 v1 square, and the velocity of the target m2 is v2, so its kinetic energy is half m2 v2 square. So the total kinetic energy of the colliding system after collision will be what? That will be half m1 v1 square plus half m2 v2 square. So this third equation we have obtained by applying the principle of conservation of kinetic energy, because the collision is elastic. This this equation cannot be written in case of inelastic collision, because in case of inelastic collision, kinetic energy before and after collision are not equal. But when the collision is elastic, you know the kinetic energy before collision and the kinetic energy after collision of the colliding system are equal. Okay, so in this way you can see we have obtained three independent equations, that is equation number 1, this equation number 2, and this equation number 3. Okay, now see these three equations seriously. Actually, in a proper physical problem, in general, masses of the particles are given. So you can say that in most of the problem, these m1 and m2 are known. These are known. Okay. So in general, masses of the particle are not needed to be calculated. Okay. But except m1 and m2, what are the quantities present in these three equations? You can see there are actually three velocities. First one is u1, another is v1 and v2, where u1 you can say this is initial velocity, v1 and v2 are final velocity. So this is as a whole 3. So there are 3 velocities in these 3 equations, and apart from these 3 velocities, there are 2 angles, theta 1 and theta 2. These are angle of scattering and angle of recoil. So as a whole, you can say there are 2 angles here. So in fact, in this condition, you can say if we think that if we think that sorry, yes, now it is okay. These are 2 quantities here. So as a whole, there are total 5 quantities in these 3 equations. As you know, if we have 3 independent equations, we can find at most 3 unknown quantities. At most. If one quantity is needed to be found, that will be very easier. If 2 quantities are needed to be found, that will be also very easier. But when we need to find 4 quantities, it means 4 quantities are unknown. You cannot solve these 3 equations because the number of unknowns which can be found by solving the equations must not exceed the number of independent equations. So if among these 5 quantities any 3 are given, any 2 are given, not 3, then you will be able to find the remaining 3. It means if, let us consider, we know all these 3 velocities, then we can easily find what will be theta 1 and theta 2. If you know, let us say, v1, v2 and theta 1, then you can find u1 and theta 2. It means among these 5 quantities, if any 2 quantities are known, the remaining 3 can be easily found. Okay. So when there will be a proper problem, definitely something will be given and something will be to found. Okay. So I have written it here that it is possible to find the unknown quantities by solving the above 3 equations. But the solution in lab frame is not very easier. It is a tedious process. It is a complicated process. Okay. So in practice or in practical, you can say that handling this problem in center of mass force is easier than in case of the laboratory frame of reference. Okay. So when you will solve such type of problem in center of mass frame, which you will see in my next video, then you will see that the solution of problems become very easy or very convenient when we do not solve the problem in laboratory frame but in center of mass frame. Okay. It does not mean that we cannot handle the problem in lab frame. In lab frame we can handle the problem, but it is more convenient to handle such problems in center of mass frame, which is the subject matter of my next video, when we will discuss the same problem in the next video. Here I am just illustrating this idea by taking a very simple example. Let us consider that in the above example which we have just seen, if you are given that the masses of the two particles are equal, it means m1 is equal to m2, then you can show that the sum of these two angles, theta 1 plus theta 2, that will be equal to pi by 2. Or you can say, when a particle, let us say of mass m, is at rest, and another particle of same mass m collides with this second particle, then after collision the projectile and the target will move at right angle to one another. It means when you say that this projectile is moving in this direction and the target is moving in this direction, then this angle will be equal to pi by 2. In other words, you can say that theta 1 plus theta 2 is equal to pi by 2. You can see how easily we can solve this problem, or we can prove this result. What you have to prove? You have to prove that if the masses of two colliding bodies are equal, then the velocities of the colliding bodies after collision will make an angle pi by 2 with one another, or the projectile and the target will move at right angle after collision. This we have to show. But this will happen when the collision is elastic and masses of these two colliding bodies are equal. You can see, applying the same two conservation principles, we can easily solve this problem. I am not following the results which we have obtained earlier. I am solving this problem independently. You can see, as you know, in any type of collision, either elastic collision or inelastic collision, total linear momentum of the system remains conserved, which means total linear momentum of the colliding system before collision and after collision are equal. So I have written here, on the basis of momentum conservation, Pi is equal to Pf. Here I stands for initial and F stands for final, which means the total linear momentum vector before collision is equal to total linear momentum vector after collision. Okay. I have written here this equation in vector form. Okay. In this form, actually the solution will be more easier. But you know, before collision only mass m1 is moving with velocity u1. So the momentum before collision is m1 u1, because u2 is 0. And after collision, velocity of m1 is v1, so its momentum will be m1 v1, and that of m2 is v2, so its momentum is m2 v2. So you can write, on the basis of principle of conservation of linear momentum, that m1 u1 is equal to m1 v1 plus m2 v2. But as in our problem it has been mentioned that the masses of the two particles are equal, so you can say that m1 is equal to m2, and we have considered that this m1 m2 both are equal to m, let us say. So instead of m1 and m2, now write down m, and so you can say that this is m u1, and in RHS we will take m as a common factor. Okay, so this is m1 m u1 equal to m times v1 plus v2. Now these two m will cancel out, and your result is u1 equal to v1 plus v2. Okay, you can see on the basis of equation 1, you can say that this u1 vector is obtained after adding vectorially v1 and v2. So you can say that u1 vector is the resultant of vectors v1 and v2. Okay. This equation we have obtained by applying the principle of conservation of linear momentum. Now let us apply the principle of conservation of kinetic energy, because the collision is elastic. So you know, in elastic collision, total kinetic energy of the colliding system before collision, that is summation ki, is equal to total kinetic energy of the colliding system after collision, that is summation ki. But what will be total kinetic energy before collision? That will be simply half m1 u1 square, because u2 is 0. And after collision, the total kinetic energy will be half m v1 square plus half m v2 square, because mass of both of the particles are equal. So I have written everywhere m. Now you can see this half m will cancel out, because it is a common factor in both LHS and RHS. And so you can write this equation as u1 square equal to v1 square plus v2 square. Okay. Now, as I have told you earlier, see this equation 1, u1 is just the vector sum of v1 and v2. It means u1 is called resultant of vector v1 and v2. And you know from triangle law of vector addition that if u1 is the resultant of vectors v1 and v2, then the modulus of u1 is found how? If u1 is the modulus of resultant u1, then you know from triangle of addition that this u1 square will be equal to v1 square plus v2 square plus 2v1 v2 cosine of the angle between v1 and v2. But you have seen that angle between this v2 and v1 is equal to what? This is actually equal to theta 1 plus theta 2. So I have written here cos theta 1 plus theta 2. Now see this equation 2 and equation 3. You can see LHS of both of these equations are same, so their RHS will be also equal. So let us equate these two equations, and for equating those two equations you can write that v1 square plus v2 square plus 2v1 v2 cos theta 1 plus theta 2, that will be equal to v1 square plus v2 square. Okay. Now you can see these v1 square and v2 square in both sides will cancel out, and our result will be 2v1 v2 cos theta 1 plus theta 2 equal to 0. But since 2v1 v2 is not equal to 0, that means cos theta 1 plus theta 2 will be equal to 0. And if cos theta 1 plus theta 2 is 0, it means what? It means theta 1 plus theta 2 is equal to pi by 2. So you can see how easily we have solved this problem, that when a particle of mass m collides with a stationary particle of the same mass and the collision is elastic, after collision the two bodies move making an angle of pi by 2 with one another. So you can say the final velocity of the two bodies which are v1 and v2, they are perpendicular to one another. I think you have clearly understand this, and as I have told you earlier that in the forthcoming lecture we will see the same problem but in center of mass frame, where we will also relate the angle of scattering and angle of recoil in the two frame of references. Okay, thank you very much.